Now we shall see Mason's rule, which was developed in 1953. The block diagram reduction technique requires successive application of fundamental relationship in order to arrive at the system transfer function. Now, on the other hand, the Mason's rule for reducing a signal flow graph to a single transfer function requires the application of one formula. That is important. We need only one formula to derive the transfer function. The formula was derived by S.J. Mason when he related the signal flow graph to the simultaneous equation that can be written from the graph. Now, we'll see what is Mason's rule. The transfer function C of S by R of S of a system represented by a signal flow graph is given by C of S by R of S is equal to sigma I equal to 1 to n pi into delta I by delta, where n is the number of forward paths, pi is the ith forward path gain, delta is the determinant of the system, and delta I is the determinant of the ith forward path. C of S by R of S is output by input in S domain, and it is called the transfer function. With this formula, with this single formula, we can calculate the gain of the system. Now, delta is called the signal flow graph determinant, or it is called the characteristic function. Since delta is equal to 0 is the system characteristic equation. C of S by R of S is equal to sigma I equal to 1 to n pi into delta I by delta. In order to calculate delta, the formula is delta is equal to 1 minus sum of all individual loop gains plus sum of the product of the gain of all possible two loops that does not touch each other, sum of the product of the gains of all possible three loops that does not touch each other, plus the fourth minus the fifth, and so on. Now, delta I is the value of delta for the part of the block diagram that does not touch the ith forward path. Delta I is considered to be 1 if there are no non-touching loops to the ith path. Now, let's see an example. In this example, we have to apply Mason's rule to calculate the transfer function of the system, and it is represented by the signal flow graph shown in figure. The first step that we have to do is to find the forward path of this given diagram. Now, looking at this diagram, we know there are basically two forward paths. The first one is G1, G4, H2. It travels from the input node to the output node without crossing any node more than once. So the first forward path is G1, G4 into G2, and the second forward path is this from R, G1, G4, G3 to C. So this is the second forward path. So therefore there are two forward paths. So n is equal to 2. The sigma I is equal to 1 to 2 pi into delta I, or which forms C by R is equal to P1 delta 1 plus P2 delta 2 by delta. Now L1, L2 and L3 are the three loop gains, individual loop gains. So basically there are three loops here. This is the first loop, and its loop gain is G1, G4 into H1. Second one is this loop, which is G1, G4, G2 minus H2. So G1, G2, G4 minus H2, and the final one is G1, G4, G3 minus H2. So there are three individual loops, and L1, L2, L3 are loop gains. So delta can be calculated using loop gains, and delta is there are no non-touching loops, therefore delta is equal to 1 minus sum of all individual loop gains. So delta is equal to 1 minus L1 plus L2 plus L3. We already calculated L1, L2 and L3. So we have the equation 1 minus G1, G4, H1 minus G1, G2, G4, H2 minus G1, G3, G4 and H2. Now next is the calculation of delta 1 and delta 2. Now, in the forward path 1, there are no part of the graph which is not touching the first forward path. So delta 1 is equal to 1 and delta 2 is also equal to 1. So our equation reduces to C by R is equal to P1 delta 1 plus P2 delta 2 by delta. Delta 1 and delta 2 is equal to 1. We have two forward paths, which is G1, G2, G4 plus G1, G3, G4 by delta is 1 minus sum of individual loop gains. We have three loop gains, which is represented by G1, G4, H1, G1, G2, G4, H2, and G1, G3, G4, and H2. So finally, we arrive at the transfer function of this equation, of this signal flow graph using a single equation. So that is an advantage of Mason's rule. Thank you.